Hey guys, this is Mr. Lowry. Today in class we worked on one of our zombie day activities, which was called Z plus 3, and it was basically comparing linear and exponential functions. It looks something like this, and in this activity we had a graph, a table, and we wrote some functions. So that's what we did in class. Now, your homework for tonight is this guy, linear versus exponential functions, but this builds on some of the ideas that we talked about in that activity. So if you miss class and you haven't done that activity, you should go back and do that activity first and work through that one because the ideas there are going to be important. But I also, before we start this, want to just kind of talk about some key concepts about linear functions and exponential functions so that this will make a little bit more sense. Okay? So we're going to kind of make a list here, linear on one side, exponential on the other. And this would be a good thing to add to your notes so you could use on tests and quizzes and things like that. But again, this is some stuff that we kind of talked about today. The first thing that we want to talk about is how do we write an equation for a linear and for an exponential function. Okay? Linear has a few different formats that we've talked about, but probably the most common is slope-intercept form, which looks like this, y equals mx plus b. What we know about this is m is the slope, okay, and b is the y-intercept. Okay? Another thing that we know about linear functions is that have a constant rate of change, and you can see that in the slope. So sometimes slope is referred to as a constant rate of change. Slope is a rate of change. So linear functions have a constant rate of change. Okay. Also, the y-intercept is another way to think about the y-intercept is as your initial amount, just like we did with exponential. So y-intercept or initial amount, your starting amount. Okay, so that's what the equations look like. For exponential, they look something like this, a times b to the x power. Okay, and we know that a is the initial amount, or in other words, your y-intercept. Okay, and then this b, it's different from this b is your growth or decay factor. And it's the number you're multiplying by. So exponential functions do not have a constant rate of change. What they do have is they have a growth or decay factor. And the difference is a constant rate of change means you're adding or subtracting the same number every single time, whereas a growth or decay factor means you're multiplying by the same number every single time. And I'll point that out a little bit later as we look at some graphs. Okay, so that's the difference in what the functions look like. Now let's take a look at some graphs. Okay, how do they differ? So we're going to do a graph for an exponential and a graph for a linear. Okay, well, linear means line, right? So when you graph a linear function, it should look like a line. So if we have an axis kind of like this is similar to like what we did in class today. You might see a linear function that looks something like this. Okay. Now this line, no matter where you go, it always has the same slope. The slope does not change. So you see the constant rate of change in the fact that it's always the same slope, no matter what. That constant rate of change and the slope are kind of synonymous. They mean the same thing. Okay? Now the graph of an exponential function, it can go up or it could go down. It kind of depends. But if we're talking about exponential growth, which is kind of what we were working with today in class, it looks like this. Okay? Notice it is not a straight line. It does not have a constant rate of change. It doesn't have the same slope every time. It actually gets steeper as it goes. This is always the same steepness. This starts out like not super steep, and then it gets steep as it goes up. So this graph grows faster in the steeper section, and it's growing slower in the flatter section. Whereas this guy is always growing at the same rate, that constant rate of change. Okay? Let's look at some tables now. Okay? And how they differ from a table perspective. Okay, I'm going to make a couple tables. We'll do a linear one and we'll do a exponential one. We may even do more than that, but we'll take a look here. Okay, so let's see what we got. Let's say I had 0, 1, 2, 3, 4. And then over here I had 5, 9, 13, 17, 21, something like that. What you see here is that there's a pattern of adding the same number every time, right? This is a +4, this is a +4, this is a +4, this is a +4, right? That's the constant rate of change. We're adding the same number every single time, okay? Now, if we look at a table for an exponential function, we are going to see a pattern, but it's a different kind of pattern. Okay, in an exponential function, we're going to have something like this. Let's say we have 5, and then we have, let's do 10, and then 20, and then 40, and then 80. Okay, this pattern is doubling. We're not adding the same number every time. What we're doing is we're multiplying by the same number every time. Okay, we're doubling. So this is an add pattern, this is a multiply pattern, and that's how you can tell the difference. Now sometimes you can have, like in a linear function, the number you could be adding could be negative, or in other words, it could be a subtraction problem. You can also, you don't have to go by ones over here. So let's take a look at a couple examples that look like that, because this will help us on our homework. So let's do another linear table. Again, this is the linear side, x, y. Okay, and let's say we had like -2, 0, 2, 4. Okay, and over here we had like, let's do 5. Let's do that same one we did, 9, 13, 17. Okay, now what we want to look at here is the change in y over the change in x, because remember the slope, change in y over change in x, right? So if we look at this pattern, +4, +4, +4, you can see that it's linear because we're adding the same number every time. But the constant rate of change, or the slope, is not 4. It looks like it's 4. But if you look over here, we're adding by 2 every time, right? +2, +2, +2. So if you compare the rate of change, we're going up 4 every time we go over 2. And if you do 4 over 2 and you simplify, it's really a constant rate of change of 2 over 1. So to get the slope here, 4 over 2, 4 over 2, 4 over 2, you're going to simplify. Okay, so that's how you find the constant rate of change. It is linear because we're adding the same number every time. It's just that the slope, or the constant rate of change, is not necessarily this number. It's the ratio of these two changes. Okay, the reason why we didn't worry about that over here was because these were +1, +1, +1, +1. X was going up by 1. And so if I write 4 over 1, 4 over 1, 4 over 1, that's still equal to 4. So it kind of depends on what our x's are doing. Okay, so this is linear. The constant rate of change is 4. This is linear. The constant rate of change is 2. Okay, in other words, the slope. Okay, let's look at one more linear and see what's going on there. And we'll also look at one more exponential. Okay, let's say I had -3, 0, 3, 6. Okay, and let's say I had, let's go 16, 10, 4, -2. Okay, and we want to tell if this is linear. Well, check out what's happening. We're actually getting smaller, and that's okay. Every time we're subtracting 6, and that's still linear. It's still kind of that constant rate of change idea. So it's an adding or a subtracting pattern. Okay, now over here, what's happening is I'm increasing by 3 every time. So if you want to know what the constant rate of change is, it's -6 over 3, which simplifies to -2. Okay, so you can see that it's a constant rate of change because it's a subtracting pattern, but the constant rate of change is the change in y over the change in x. If you remember our slope formula, it looked something like this. y2 minus y1 over x2 minus x1. So if I do y2 minus y1, that's negative 6. x2 minus x1, that's 3. And I get negative 6 over 3, which is negative 2. Okay, so the constant rate of change is change in y over change in x. Or basically slope, right? Okay, let's look at one more exponential so we can kind of take a look at this pattern. Okay, so let's go, we'll just do 0, 1, 2, 3, 4 again. Okay, and let's go 100, 50, 25, 12.5, and let's just stop there. Okay. Now what we're doing here is it looks like we're dividing, right? And that's true in a sense. We're dividing by 2 because it's halving, but dividing by 2 is the same as multiplying by a half. So even though this guy is going down, we're multiplying by the same amount every single time. Okay, so exponential is a multiply or divide pattern, but we typically write it as multiplication. Linear is an add or subtract pattern. But remember, if you want the constant rate of change, you need the change in y over the change in x. Okay? Some of the questions on your homework will ask you about tables and stuff and determining, if it's linear or not. Let's take a look at that homework now. All right. So here we have two functions that we need to graph, and we have to remember how to graph each of these. Now the first guy is linear, and the second guy is exponential. Okay? To graph a linear function, we start with the y-intercept. Okay? There's your y-intercept. Now, this was kind of my bad because I didn't make this graph quite low enough. So let's add one more line. This was just oversight on my part. Okay. Now notice that this graph goes by 2's. So I'm going to make this negative 4. Okay. So negative 3 will be halfway in between negative 2 and negative 4. So something like that. Okay. So that's the y-intercept. Now this is the slope, right? 10 or 10 over 1. So this guy goes up 10, right 1, up 10, right 1, up 10, right 1. So if I'm at negative 3 and I go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over 1, I'm going to be here at 1, 7. Okay? Now remember, these are going by 2's, so don't count 1, 2, 3, 4, because that's not going to work. You got 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is scaled by 2's. Zoom in a little bit so you can see this better. Okay, so let's do it again. We're going to go up 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over 1. So it looks like we're at 17. Let's do it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over 1. Okay, that gives us a pretty good idea of what our graph's going to look like. So if we connect those guys, there's our linear function, right? It's got a constant rate of change. The constant rate of change is 10 over 1, 10 over 1, 10 over 1. We see that with the slope. It's a constant slope. It doesn't change. It's the same steepness all the way through. Okay? So linear functions have a constant rate of change, which is why they look like a line. They don't curve at all. That's an important concept. Okay, the next one's exponential. In order to graph an exponential, we need a couple things. We need an initial amount, and we need a growth or decay factor. Okay? Now, this function doesn't look like it has an initial amount. It looks like it just has a growth factor. So what we need to do is we need to maybe rewrite it as 1 times 3 to the x. If you don't see an initial amount there, then it's probably that invisible 1. So we're starting with like 1, I don't know, zombie or whatever, and then it's tripling every time. Okay? So we're going to start at 1, which is right here. And then every time we move over, we're going to triple the value. Okay, so right now we're at 1. We're going to triple it. 1 times 3 is 3. So when we move over 1, we're now going to be up at 3. And then we're going to triple again. So we're going to take that 3 and we're going to multiply it by 3, and we're going to have 9. So when we move over 1 to the right again, we're going to be up here at 9. halfway in between 8 and 10. And then we're going to do that again. 9 times 3 equals 27. Okay, so when we move over to 3, we're going to be all the way up here at 27, right? And notice that that's also a point on the linear graph. Okay, so if I connect these guys, it's going to be something kind of like this. It's going to go steeper, 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 boom, and they're going to cross right about there. Okay, in our zombie activity, that was where the zombies passed the humans. Okay, now our graph keeps going. It's just going to get closer to the x-axis down here. It's going to get smaller and smaller and smaller, kind of level out. Right? So those are our two functions. We've talked about how to graph exponential functions before. Start with the initial value and then use your growth or decay factor, multiply to get the next values. Linear is old news. We know how to do that. The only tricky part about this one was the y-intercept was a little bit too low, which was my fault. Okay. Where is the exponential function greater or higher than the linear function? Okay. Well, it passes it here, so but it's also a little bit higher here. So it's a little bit, it's higher than it, between 0 and 1, right? And then it's higher than it after 3. So we can kind of use words to do that, or we can use like interval notation. So this is, it's actually higher all over here too. So from negative infinity all the way up to around here, it's higher than the linear, right? The linear is below it. So from negative infinity forever and ever all the way until we hit this point, which is about, I don't know, half maybe. We are bigger than the linear. But then the linear takes over for a while. So from about 1/2 here all the way until 3, the linear rules. The linear is in charge. It's bigger. It's above the other one. Okay. Then later, the exponential overtakes the linear again. So from 3 out to infinity, going this way, everything after 3, the exponential function is going to be greater. So something like this. Okay. We tie those together with a little union symbol. Okay, so that's the interval. Now, if you didn't want to write an interval, you could describe that. You could say any time before x is 0.5, the exponential is bigger, but then anything after 3, the exponential is also bigger. So something like that. But that's kind of the idea. Okay, which of the functions have a constant rate of change, and what is the constant rate of change? Well, it's the linear one, right? It's the one that's a straight line. That constant rate of change we can see right here. 10 over 1, 10 over 1, 10 over 1. It's always 10 over 1. Stays straight the whole time. So the linear function, which is the y equals 10x minus 3, that's the function that has a constant rate of change because it's linear. And then the constant rate of change, I'm going to do CROC, croc for constant rate of change, is equal to 10. And remember, that's the slope. It's the same thing as slope. Okay? So you could also say m equals 10, because m is the letter we use for slope when we write y equals mx plus b. Okay, how can you see that the function has a constant rate of change by looking at its graph? So you could say it's a straight line. Slope doesn't change. Right? It's not curvy. Straight line means that the slope is always the same. So yeah, you're just looking at it, you notice it's linear. It's a straight line. Okay. Where is the linear function growing faster than the exponential function? Okay. And this has to do with how steep they are. So right now, this is really shallow. It's not very steep. This just gets started really slowly. And then as it gets steeper, that means it's growing faster and faster and faster and faster and faster. So, where does it start to get steeper than the line? Well, right about here is when they start to match, and then it starts getting steeper. So this is going to be some estimation, right? But here it's like it's not as steep, not as steep, not as steep, not as steep. Then it's about the same steepness, and then it gets steeper. So if it's growing faster on the graph means steeper. Where is it steeper? Okay. So it's somewhere in between 2 and 3 where the graph starts getting steeper. Now, of course, it passes the graph. It's higher than the graph at 3, but it starts getting steeper around 2, 2.5 maybe is where it starts to get steeper. So I'm going to say from about 2.5 to infinity is where it is steeper, right? How can you tell? The exponential, just so you can see it, graph is steeper after 2.5. Okay. Now, if you think about it in terms of like zombies and stuff, this would be like after 2.5 hours or whatever in our scenario, right? So it's like, okay, once you hit 2.5 hours, then this graph is steeper, and when you hit 3 hours, there's more zombies than humans. Okay, so there's two different questions here. One of them is talking about when is it higher. The other one's talking about when is it steeper. Okay, so steeper indicates that it's growing faster. Higher indicates that there's more, I don't know, zombies than humans or something like that. Okay. Okay, let's take a look at the back. Now we're going to use these tables to determine if the function is linear, exponential, or neither, and then we're going to find the growth factor or the rate of change depending on if it's linear or exponential. Now this is another kind of silly thing that I did. I put the same table twice. That was my bad. But let's take a look. Okay, so if we look over here and we're looking for, if it's linear, we're looking for a constant rate of change. So if I were to add 12 here, I would get to 18. If I added 12 again, I would get to 30, and that doesn't work. So it looks, if it's a linear pattern, it's the same thing every time. 6 plus 12 is 18, but 18 plus 12 is 30, not 54. So it's definitely not linear. Okay, let's try a multiplication pattern. Okay, 6 times 3 is 18. Okay, so what's 18 times 3? Let's see if that works out. So 18 times 3 is 54. Okay, cool. What's 54 times 3? 54 times 3 is 162, which doesn't make any sense. It's supposed to be 108. So what happens is I multiply by 3 and multiply by 3, and actually 54 times 2 gives me 108. And 108 times 2 gives me 216. So it starts out looking like a multiply pattern, but it's not the same number every time. It's not times 3 times 3 times 3. It's like switches halfway through. So it's not linear because we're not adding the same number every time. And it's not exponential because we're not multiplying by the same number every time. So this would be neither. Okay, let's look at the next one, number 7. Okay, looks like to get from 4 to 20, we would have to add 16 if it was linear. Okay, let's see if that pattern continues. 20 plus 16. If we add 20 to 16, we get 36, and that doesn't work because we're supposed to be at 100. So we try the adding pattern, it doesn't work, so it's not linear. Okay, let's try a multiply pattern. 4 times 5 is 20. But what's 20 times 5? Is it 100? It is. What's 100 times 5? 500. What's 500 times 5? 2500. Okay, so it is a multiply pattern. Times 5, times 5, times 5, times 5. We're multiplying by the same amount every single time. So this is exponential. And the growth factor is 5. Okay? All right. Number 8. Write a linear function that has a constant rate of change of 1/2 and an initial amount of 50. Okay, now these phrases, these are a little bit different than we're used to. Okay, but constant rate of change is the same thing as slope, and initial amount is the same thing as y-intercept. Okay, we also know that it's linear. So y equals mx plus b is the format that we're looking for. Okay, slope is m, y-intercept is b, and we just need to fill in the pieces. So y equals 1/2, right? Constant rate of change, plus, oh sorry, 1/2 x plus 50. We need an x in there. Okay, so we're using slope-intercept form. Okay, number 9, write an exponential function that has a decay factor of 1/2 and an initial amount of 50. Okay, now remember that our exponential template looks like this. This is how we write an exponential function. Okay, decay factor is b in this case. Initial amount, also y-intercept, but we call that, in this case, y-intercept is the a piece. Okay. So we got f of x equals 50 initial amount times 1/2 to the x power. Okay, notice how they both use the same two numbers. It's on purpose so that you can kind of see the difference. Okay, constant rate of change does not have an exponent. That's 1/2 times x, right? This is 1/2 to the x power. Okay, one's linear, one is exponential. Okay, in your own words, explain the difference between exponential and linear. Well, now you have a lot of language to do that. We've talked a lot about the difference between them. Okay, you have some words here that you can use, some phrases that you can use. So talk about how they grow, talk about rates of change. There's lots of different ways to kind of discuss that, but I'm going to leave that up to you to use your own words there. Okay, next up, we're going to write a function equation that represents the pattern. Okay, the first thing we might want to do is find out if it's linear or exponential. Okay, now in this case, we got x's go by 1, 0, 1, 2, 3. Okay, that's pretty convenient. So let's just look at the y's here. If I'm looking at this pattern, this looks to me like an add pattern. Plus 3, plus 3, plus 3, plus 3. Right? It's the same every single time. So my constant rate of change is 3 over 1, right? My x's are going plus 1, plus 1, plus 1. Okay. So my constant rate of change, or my slope, is equal to 3 over 1. Right? Change in y over change in x, or just 3. Okay. My y-intercept, or initial value, is right there. It's 12. When x is 0, y is 12. Or, in other words, we're at 12 on the y-axis. Or when 0 time has gone by, we have 12 zombies, or whatever it happens to be. So your y-intercept here is equal to 12. And this is linear, right? Constant rate of change. We're adding the same thing every time. So y equals mx plus b, right? Y equals 3x, 3 over 1 is our constant rate of change, plus our initial amount, our starting amount. Y equals 3x plus 12. Right? This is linear. Now, it doesn't ask you to do this, but we might as well label that one linear because it's got a constant rate of change. All right, let's look at 12. Okay, obviously it's not an adding pattern because it would have to be plus 20 to get from 10 to 30. 10 plus 20 is 30, but 30 plus 20 is 50, and that's not working here. So instead, what we need to look at is what factor. What are we multiplying by? All right, 10 times 3 is 30. Is 30 times 3 90? Turns out it is. Okay, what about 90 times 3? That better be 270. So double check to make sure it is. And it turns out it is. Okay, so this is my growth factor. Okay, this is an exponential function. It's a multiply pattern, right? This is a plus 3, plus 3, plus 3. This is a times 3, times 3, times 3. Okay, linear, constant rate of change, adding the same thing every time. Exponential. It's not a constant rate of change. We're not adding the same thing every time, but we are multiplying by the same number. So that's called a growth factor. So remember that my form looks like this, a times b to the x, where this is the initial amount and this is the growth or decay factor. Okay, we already know our growth factor is 3. If we look for our initial amount, it's again our y-intercept, our starting amount, or our value when x is 0. No time has gone by. We have 10 zombies or whatever. Okay, so that's my exponential function. I'm just going to add an f of x. And there you go. Okay, so lots of compare and contrast here with linear and exponential. We're good at linear, we've studied linear, we're comfortable with linear. The new thing is exponential, and now comparing, how are they different, how are they similar, what's the big deal, okay? So that will get you through your homework. We did all of them there, so if you're a little confused still on exponential versus linear, that will kind of help you get the rest of that assignment. We'll talk more about this next week. We'll finish up our Z+3 activity if you're in class. If you're at home and you missed that, then you, again, I need to do it at home. And we'll kind of put some of the pieces together next week as we keep talking about exponential functions.